So hey guys, so I don't know which day it is, but I guess this is day 8 of solving programming problems. So today we are going to take a look at one of the one of the trickiest problem in Gigs for Gigs. This is to find the problem is to find kth smallest element in an array. So when I first took a look at this problem, it seemed pretty straightforward. Like the idea is to find the kth smallest element, right? So the obvious solution would be to sort the array and then find the kth index in the array. So that way we'll be able to return the kth smallest element. So I started to write out the most obvious solution. You just like put arrays.sort and then you return arrays.get of k minus 1 and you would get the k smallest element. But when I scrolled down a bit further, I found that you had to solve the problem in order of n time complexity. So sorting takes n log n time complexity, so I'm not supposed to be using that. But I was looking at probable solution to solve this problem, and one of the probable solution was to make use of a sorting algorithm called quicksort. And the idea is to use a part of quicksort's algorithm to be able to find uh, the kth smallest element. So uh, what we would do is that we get an array, right? So we get an array of elements, and we're supposed to find the third smallest element. So the idea is to initially partition the elements by using quicksort's partition algorithm. So we would start by if you knew quicksort's algorithm, so what we would do is we would start by taking in a pivot element. Uh, the way that we select a pivot element is just by randomly taking in an element. Just for the sake of this example, we're going to take the first element to be our pivot element, and then we would have two indexes in the array. So one of the indexes would be the start index, and the other index would be the end index. So this is the idea of partitioning the array. So the idea is to find a partition point in the array where all the elements to the left side of the partition element is lesser than the partition element, and all the elements that are on the right side of the partition element is greater than the partition element, right? So we would start by doing this, and what we would do is that we would check if the element at position start is lesser than or equal to the pivot element. So if this condition is satisfied, we would increment the start element to the next index. And for the end index, what we would check is that we would check if the element at position index is greater than pivot element, and if it is greater than the pivot element, we would decrement the value of end index. So if we did do that, so what would happen? So initially we have 7 here, and we would check it with the pivot element. So 7 is lesser than or equal to the pivot element. So we would increment the start pointer to the next element. And likewise, we would compare 10 with the pivot element. So 10 is greater than the pivot element, so we are not going to do anything else here. So we're just going to update the start index to this position. So start is pretty hard to write, so I'm just gonna write S from here on now. And then once we are fixed on the start element, we couldn't go any further. We'll start with the end element, and we would compare the element at end position with the pivot element. So end is greater than the pivot element here. So in this case, we are going to decrement the index of end to here. And then we are comparing end with the pivot element. So end again is higher than the pivot element, so we are decrementing the end index. So we are arriving here. So at this point, 3 is not greater than the pivot element, so we're going to stop right now. And so once we have stopped both start and end, we are going to swap both these elements right here. So what would happen to the array? We would get this new array with 7, 3, 4, 10, 20, oops, and 15, right? So we would get this new array elements, and we were having start at this position and end at this position, right? And then the pivot was at 7. So we are going to start iterating again. So what we're going to do is that we're going to compare start with pivot again. So it's the same condition. So if start is less than the pivot, we're going to increment the start index to the next position. And in this case, again, it's less than pivot, so we're going to increment the start position to here. Again, so 10 is higher, greater than the pivot element 7, so we're going to stop incrementing start, and we're going to compare end with the pivot element. So end is higher than the pivot element, so we are going to decrement the end to the next previous thing. So end will come here. So we are now going to compare 4 with 7. So 4 is lesser than the pivot element, so we are not going to decrement end. So in this case, we are going to stop the iteration right here. And then we are going to check, before we do the swap of end and start, we are going to check if start is lesser than end. So we are going to swap only if start is lesser than end. So if at all start is not lesser than end, what we have found is the pivot, the partition position of the array for 7, right? So what we're going to do in this case, in the case of start not being lesser than end, we are going to swap the elements at position P and the element at position end, right? So end was at 4, so I'm just gonna erase all this, I guess, and end was here, right? So this is the new pointer location. So what we're going to do is that we are going to swap the position at P and E. So the new array would be 4, 3, 7, and then 10, 20, and 15, right? So this is the new array. So the partition element that we're going to return is at this point 7. So we found the sorted position of the element 7 in the array, and what does it mean exactly? So what it means is that all the elements that are before 7 are lesser than 7, and all the elements that are next to 7 are greater than 7. So this is the point of finding the partition position. And so once we find the partitioning position in the array, we will essentially return the element index, right? So right now we found the partitioning for index 3. So we will return this index from, say, a partition method, and we will compare it with the value of k. So we're supposed to find the kth smallest element. So we will return the index index from the partitioning method, and we will compare it with the value that we're supposed to find, right? So in this case, we returned 3, and we were supposed to find the third third smallest element in the array. So during the initial iteration, we were able to find the index. So so the output, so the position at 3 is 7. So we were able to say that 7 is the third smallest element in the array, and we were able to figure out that 7 is indeed the third smallest element in the array. So this is the basic idea of solving this problem. So I'm going to go through the Java code right now of solving this problem. So initially we were given with this method. Uh, so we are going to cover a few base cases here. So if at all so L and R, L is the first position and R is the last index position of the array, and K is the number of the smallest element that we're supposed to find out. So we are initially checking if L and R are equal, meaning that we just have one element in the array. If at all we do have just one element in the array, and we are going to if at all we do have just one element in the array, we are also going to check if that one element is the element that's being asked from us, right? So k minus 1 is the index. In this case, we're just going to return the only one element that we have, right? So ARR of L. So the next method that we're going to call is the partitioning algorithm that we just talked about. So we are going to find a partitioning position within the array from the left and the right, and for the array. We are going to find the partitioning position of the array, and we are going to check if the partitioning that we found is equal to the kth element that we want. So if at all if it is equal to the kth position, we are going to return the array value, or else we are going to check if it is lesser than the kth position that we want. If the partitioning position that we found is lesser than the kth position that we want, we are going to take the leftmost subarray, meaning that if 7 is was the partition that we found, right? If it is not the position that we want, and if the position that we want, for example, is 1 and we found 2, we need to check the leftmost arrays again. So we are going to recurrently call the left array, left array, if it is if the pivot is lesser than, or else we are going to call the right array to find it. So likewise we'll do recursive calls again and again to figure out which position that we are in search of, and once we do that we are going to do a return. So by that way we'll just be able to return at the end of this, we're just going to return the array position through here. So that is it. So yeah, so the partition algorithm is here. So we are iterating from start to the end up until start is lesser than equal to end. So we are iterating, we are comparing the pivot element with the start. If it is lesser than that, we are incrementing it. Likewise, we are doing the n minus minus, and we are doing a swap here. And by the end of this iteration, we are swapping the first element, meaning the pivot element, with the leftmost element, and then we are returning the end, meaning the partitioning position. So this is what we are getting at here, this location here. So that is it, guys. See you again tomorrow for the next problem.